Hi, today we are going to learn how to train your own custom dataset using Detectron2. We will do the full cycle from the data annotations, coding the training process, and running an inference on a new and fresh image. So first of all the installation will be in my previous video tutorial, so this is the link. And this video is part of an object detection playlist, so you can cover more tutorials in this link. First of all, our tutorial will be divided to several steps, and the most important issue is, please notice that our home directory here in the VS Code is the Detectron2, the one that we installed earlier. And the first step will be the annotations of our images. So let's, for example, open our train images. As you can see, we have here several images. This is a strawberry, and this is a banana, and we have grapes. And basically we need to annotate. What annotate means that we have to place dots as a polygon dots around each of those objects. Here we have to make dots around those lemons, those 4 lemons, and the same in the other images. So I have here the first step is doing this annotation process. I've left here instructions. Of course, all these files will be part of the code. I will leave a link in the video description for the code and all the links. So let's copy the link and open a browser. As you can see, this one, Make Sense, is a website that enables you to annotate all the objects on your custom dataset. So let's get started. First of all, we will have to upload our images. We will click here. As you can see, this is the folder for the train images. You should look for your images as well. I've chose the train. We have here the test. The test doesn't need any annotations, so it will be our test images to run the inference of our model, but we need to annotate the train images and the validation images as well. So how can we do it? We choose the train images. We have to choose all the images with Ctrl A and click the open button. As you can see, 12 images loaded, and then we have to choose our problem. In our case, it would be object detection. So let's click here the object detection, and the next phase is creating our labels. So let's add our labels. We have an apple and strawberry. The next one is orange, and the next one is grapes, banana, and lemon. So basically we have 6 different categories. Now let's start our project. We have to choose here on the right bottom side, we have to choose a polygon. It's very important. Then we will start and using the left click of the mouse, the left button, and we will do the annotation with adding dots around each of the objects. Let's start with this first strawberry. We have to finish the full cycle and then choose a label, in our case a strawberry. Then let's add another one. So basically it's only one work that so basically we have to do it one time only and annotate all our images. So the next object is a strawberry as well. Now let's choose the next one. So this is the next one, and let's, for example, choose another object like this one, an apple. Once again, we have to put dots around our object. Wait a few more seconds and we create this polygon till the first one, this one, and now we have to choose instead of strawberry an apple. So let's choose this one, and we have to do the same for these two objects as well. After you finish doing all the annotations, you have to click the actions and then export annotations. Click here, use the Coco JSON file and export the file. Basically, it generates a JSON file for these train images. If I will close the browser, you can see that I've already done this process, and we have a JSON file with for all the train images and another JSON file for the validation images. So you can use my JSON file or create your own for your own dataset, but it's very important that the JSON file will be along with the images in the same folder. So as you can see, we have a fruit folder with the test, train, and validation. The trains contain the images with the JSON file, and the validation contains the validation images with the JSON file, and the test, of course, contains only 2 test images that we will examine test our model after the training process. Basically, we will try to detect if this is a banana or an apple, and to take these objects in this test image. So as promised, I will leave this instruction file. As you can see, this is the link for creating those annotations. I left some instructions. All the images should be on this subfolder. You can see it here as well. And inside this folder, we create another one, fruits for Detectron2. These are the 6 labels, our 6 categories: apple, strawberry, orange, grapes, banana, and lemon. Then we should open the link. We should open the link in our browser, upload our train images, choose object detection problem. Then we have to select a polygon, and after doing all the annotation process, we have to choose actions in the menu and export annotation and choose a Coco format. Then you should copy the generated JSON file to the train images, and repeat the full process for the validation images as well. So now let's continue with discovering our train data. So basically, we would like to load some of the images and the annotations and merge them together on one image. So let's create a new Python file. Let's call it step number 2, load the data. We will start with importing some libraries. Of course, the Detectron2. We should also import NumPy and OpenCV. And for visual our image, using the annotation, we will load some more instances and objects from the Detectron2, like the visualizer. We also need to import the meta catalog and the dataset catalog. These both classes store information about our dataset, including metadata like the dimensions of the images, the class labels, and basically actual data itself. Now we should register our dataset, and in order to do that, we will import the register Coco instances function. And the Detectron expects a dataset to be formatted to a specific way, often following a Coco format. So this function helps us register our custom dataset in a Coco format. So in order to do that, we will send several arguments to this function. The first one is the my dataset train. It's basically the name of, we are choosing a specific name for our train dataset, and also we will send the path for our JSON file and the path for our images. So this would be for the train dataset, and we will do the same for the validation dataset. Once again, we will register, use the register function, and we will register for the dataset validation, same as we did for the train dataset. And same, we are sending the JSON file and the folder where we store our validation images. Now we should access our metadata and the dataset information. So we will use the get function from the metadata catalog. This method retrieves the metadata associated with our training dataset. This metadata might include information about the image resolution and the class label used in our dataset. And similarly, we will use the dataset catalog .get function method to obtain the list of dictionaries, and each one of them is representing an individual image in the training dataset, and these dictionaries likely contain information like the image file name, the height, the width, and potentially annotations from object presented in the image. Okay, here we are going to access the first element, index 0, from the trained dataset dictionaries. This list contains dictionaries for each image in the training dataset, so the first dict now holds the information about the first training image. When you print it, you can see all the information stored in this variable. Great, let's continue. So now we will extract and grab information out of this first dict variable. And we start with the file name. We extract the file name of the first training image from the first dictionary and store it in the file name variable. And let's also extract more information about our image, like the height, the width, the image ID, and most important, all the annotations for the objects inside our first image. Great, now we would like to display our image along with the annotation. So first of all, we will use the OpenCV-IMRead to load the image. Then we will use the visualizer. And please notice the first argument, basically we are converting our image from a BGR format to an RGB format. And next, we use the function draw dataset dictionary, and this function or this method use our visualizer object to draw the annotations, all the bounded box and labels on the image based on the information in the first dictionary. This dictionary likely contains information about the object presented in the image, and the result would be stored in the viz variable. And then we are grabbing the image using the get image and display it using the IMShow function. So now we are expecting to see our image, the first image from the training dataset, along with the annotations. Great, so this is the result for the first process. Now let's continue to the next one, which is training our dataset. So let's start with creating a new Python file. Let's name it step 3 train custom object detection, and this would be on Windows environment. I will also add a bonus file with running this training on an Ubuntu on a Linux environment as well. So let's start with importing some Python libraries. We will once again import the register Coco instances, and we very important that we will import the default training object. We will use this default training object in order to train our images. Next, we have to use one of the Detectron pre-trained models. You should go to this website, look for the Coco object detection baseline, and look for one of these pre-trained models. I will choose this one. Of course, I will leave a link at the code for all these models, so you can choose your own pre-trained model. First of all, let's define our config file. We will choose one of the pre-trained model. I choose the R50 FPN model. So this would be our config file path, and model name we should choose the name, the same name as our config file path. Now we should define our output directory. I decide to call it my train OD Detectron2. Next, the number of classes. Basically, we have 6 categories, so we have 6 classes. Device would be CPU. If you're running on a CUDA environment, like in Linux environment, you should replace it with the text CUDA. Next, let's define some more variables. The first one is our train dataset name. Let's call it LP_train. You can choose your own name. Next, let's define a variable for the images, for the train images. I store the images, my images, in this path. And also the name of our JSON file, the path for our JSON file. Don't forget to change the direction of the slashes. If you have any problem, most likely, if you didn't find out your files, most likely it's the direction of the slashes. Let's do the same for validation dataset. So we have to put the right folder for the validation images and for the JSON file as well. Great, let's continue. Now we have to do the same as we done in the previous step. We have to register our dataset. So we will use the register Coco instances, and we will send several arguments. Name would be the name of our train dataset, the one that we have chose earlier. We name it LP_train, and very important, the path for our JSON file and the path for our train images. And let's do the same. Let's do the same for the validation dataset. Don't forget to change to the right variables. Now we have to load a very important function, get_CFG. And also we need the model_zoo. This will help us to retrieve all the weights for our model. Now we'll define a new function. Let's name it getTrainCFG. As you can see, we will send to this function several arguments, and now we will start creating this function. Great. So we will start with the merge from file folder, and we will use the model_zoo.getConfig file to load the configuration from the specific configuration file that we will send to this function. This configuration file defines various training parameters for the pre-trained model. Next, we will use the CFG model weights, and we will get the checkpoints from our model name, and this would set the path to the pre-trained model weights. Detectron2 will download automatically these weights if they are not already available. Next, we configure the dataset names for the training and the testing using the dataset train and dataset test. Next, we will define the number of worker processes for the data loading using the dataloader.numWorkers. This can help improve training speed by loading data in parallel with the training. Next, we define the number of images per batch processed during the training with the solver.ims per batch. This is a hyperparameter that can affect training speed and memory usage. Experiment with different values to find the optimal settings for your hardware and dataset size. We also set the initial learning rate, and this is another hyperparameter that controls how much the model weights are updated during the training. Next, we define the maximum number of training iterations, like epochs. This essentially determines the number of times the entire training dataset is passed through the model. And next, we set the number of object classes in the num classes parameter. This should match the num classes variable defined earlier. Next, we'll define if we are using a CPU or a GPU by the device parameter. And finally, we define the output directory for the cfg.output.dir, where we train the model and all the other outputs will be saved. And finally, the function returns the configured training configuration, our CFG variable. Next, we'll define a main function. We will create our output directory, and then we will run the getTrained CFG function and send all the required parameters. The next phase would be storing all the weights and the training process using the Pickle Python library. We will use the Pickle library to save the training configuration to a specific path. The specific path is the cfg_save_path. So all the information can be found in this path. Now we create a default training object from the Detectron2. This object encapsulates the training logic and will be used to train our model, and we provide the training configuration as an argument. Next, we call the train method on the training object, and this initializes the training process based on the provided configuration. And I believe that we are ready to train our model. So look, first of all, we have 37 images. For example, 11 of them are apples. And let's wait a few more seconds. And now you can see after 19 iterations, after 39 iterations, so the training is running. And basically I'm running it on a fast forward, and let's jump directly to the final epoch, and we will analyze the result. So the training has finished, and now as you can see, here is a summary. We have 22 images. All those 22 images are the validation images that were tested along the training. And the important thing is to look at the total loss. The total loss here is the value 0.1252. If I will go to the starting point, as you can see, in the starting point the total loss was 2.2, and here's are the iterations. So after 19 iterations it was 2.2, after 20 more iterations, so about 39 iterations of total 39, it's reduced to 2.0. And during all the training you can see that we are going up with the number of iteration, the number of epochs. Here it's about 739. The total loss reduced to 0.2397. So basically, if we are seeing a reduction in the value of total loss, it's a good direction. So the training is going very well. And we also go to here to my train OD detection 2, and we should look for this file OD, which means object detection, OD_CFG pickle, and here it is. We have to open this folder, and this is our training file. This is the most important file. It contains the results, and then the next step will be testing our model with a new and fresh image, and then we will choose one of the test images and try to predict the objects inside those images. For example, this one, a banana and an apple. We will figure out with a new and fresh image if our model was trained well. Before we continue to testing our model, I add a bonus code here, and in this code, as you can see, you can run the same training on a Linux machine. And basically, running on a Linux machine will use the GPU card in your machine, so the training will be faster. If you have a Windows, you can install a WSL Linux on your Windows. And after you install this WSL Ubuntu environment, I left here some instructions how to set up the process before the training. And in order to do that, you should create an environment in your Linux environment and then activate this environment. I name it, just for example, Detector 99. Then you should install the PyTorch, the relevant PyTorch. Detectron2 works with PyTorch 11.13, and then you should do basically similar thing for installing in the Windows environment. You should create a Detectron folder, and also you have to run this command that install the process of the Detectron environment. And then after installing and creating this environment with the Detectron2, you can run this code that runs the training for this process. This code is very similar to the Windows code. You can see minor changes. For example, the device would be CUDA and not CPU. And also there are different references for the train folders and for the JSON file, but basically it's the same process, but it would run faster under an Ubuntu environment. So great, let's continue to the next step, which is running a test image on our model. So now it's the final step, which test our model using a fresh new images. We will use our test folder that contain 2 images, and we will try to detect those images. So let's start with creating our last Python file. Let's call it step 5, test the model, and we will start with importing the default predictor class. This class allows us to use the train model to make prediction on new images. We will also import OS and pickle libraries. Then we define the path to our saved configuration file, where we store the training configuration using pickle in our previous step. We then open the file in a read binary mode and use pickle.load to load the configuration back into our CFG variable. Next step, we defined the output directory where we trained model files might be stored. Let's copy it from our previous Python file. And next we will update the CFG model weights parameter to point to the path of the model weights file within the output directory. This assumes your training saved the model weights with this file name. You should use the same file name as our previous step. Next we will set the prediction score threshold. This means the model will only predict objects with a confidence score greater than or equal to 0.4. You can adjust this value to control the trade-off between precision and recall. Next, we create the default predictor object from the Detectron2. This object encapsulates the logic for making prediction using the provided CFG file. Now we'll define a list name classes containing all the labels like apple and strawberry that the model can convert the IDs to a class names. Make sure that this list matches the order and the number in the classes in your dataset. Now we define the path to the test image, to our first test image. We will choose this one, the strawberry image. And of course, we will load this image using the OpenCV Python library. Let's also use NumPy. And once again, we will use the visualizer in order to display the image along with the predicted annotations. The image will be stored in the IM variable, and now we can run the predictions and send our image to the predictor object. So the result will be stored in the outputs variable, and let's print the outputs at the first time we run the predictions. As you can see, there is a lot of information. For example, how many instances, the height and the width of the variable, all the detected bounding boxes, the scores, and the last one is very important, the predicted classes. This value is the position, the index in our classes list. So now let's grab information out of the outputs. For example, let's get the predicted classes. Basically, these are numbers between 1 to 6. So let's print those classes. Now, as you can see, all the values 1, 1, 1, 1. Basically, 1 means strawberry. 0 is apple, 1 is strawberry, 3 is orange. So this is the position in our class names. Let's convert it to a NumPy from a PyTorch tensor to a regular NumPy array. And now let's grab the size of this NumPy. Basically, if the value is above 0, this means that something was detected. As you can see, the value is 7. So the predictions detected 7 objects inside our test image. So now let's display the results. So if our flag is above 0, we would like to grab all the predicted classes. So first of all, we will select the first predicted class label, and let's print it. Now we'll print the class name of the predicted class ID, and let's run it. As you can see, it's a strawberry. Great. And next we will do a similar process to the step that we have done before, but instead of annotation we will use our predicted classes. So we would like to merge all the predicted classes along with our test image and display it together. So we would like to display an object with the relevant predicted class, and we will use the visualizer to display it in our image. We will run the function draw instance predictions, which is part of the visualizer object, and as you can see we are sending the output variable to this function. And at last we will use the OpenCV IMShow function to display our image. If we didn't find any detected object, we can break our if statement. Okay, let's fix some syntax error and let's run it. Okay, so this is our strawberry image. As you can see, it detected some of the strawberry, not all of them. I believe that we need more training, and maybe we can play with the thresholds. But let's, for example, see the second image that contained only two objects, a banana and an apple. We just replaced the name of the image, and let's run it again. So the second image, we have an apple and the banana. The banana is object number 4 and the apple is object number 0. So thank you very much. I hope you enjoyed this tutorial. You are most welcome to subscribe. Bye bye.